Hey, my name's Samantha and I'm from Onslow College and I've worked on the problem car. The problem states, build a model car powered by an engine using an elastic, air-filled toy balloon as the energy source. Determine how the distance travelled by the car depends on relevant parameters and maximize the efficiency of the car. Here's a demonstration of the phenomenon. This video was filmed at 120 frames per second. The balloon starts to empty and the car accelerates. The balloon empties, and from there the drag force and the friction slow the car down until it stops. Here we have an example graph which shows the acceleration, and then we have a peak which is where the balloon runs out of air, and from there it decelerates. Is the definition of engine. Potential energy within a device converted to kinetic energy of that device. This was relevant within this experiment, and we changed this definition to be relevant within our testing. Distance travelled. Within our testing we used the front wheel to determine the distance travelled. And efficiency. The ratio of useful work performed by a machine or in a process to the total energy expended or heat taken in. This is a balloon car with no opening, so before you've released it, the atmospheric pressure is smaller than the internal pressure of the balloon, and opposite sides are pushing against each other, meaning that it won't deflate. There's no net force here as nothing is pushing against the balloon. And here we can see in the graph that it's at the very beginning. This is what happens when the balloon car opens. The internal pressure is still larger than the atmospheric pressure. There's a force on air because the sides aren't balanced. There's a force on the car. You have a forwards velocity because of the backwards force of the air. The drag of the car is slowing down the car, but it's not significant enough because you still have your energy coming from the deflating balloon. So therefore there's a net force forwards on the car. Therefore it accelerates. This is around here in the graph. You can see it accelerates, but it hasn't quite deflated yet. Here we can see the balloon has run out of air. The internal pressure will match the external pressure of the atmosphere. You still have a velocity forwards because you haven't run out of momentum yet, but the car keeps moving. The drag force is eventually going to slow down your car, also friction, so you have a net force backwards which will cause the car to decelerate and eventually come to a stop. This is this part of the graph, and we can see that it decelerates until it reaches a velocity of 0 meters per second. Here's our experimental setup. As you can see, we've attached a balloon to the car. We let go, it accelerates and comes to a stop. Here are the parameters we tested. We tested 3 nozzle diameters, and here are some that we could have tested, which is the balloon inflation, the balloon elasticity, meaning we'd have multiple balloons inside each other to hopefully help it deflate faster, and then we have our car mass. Here are our nozzles. So here's our prediction. Predict that as the balloon deflates, the line will steepen out on the velocity axis. Once the balloon runs out of air, the line will descend towards 0 until the car stops. Now, something we found was if the nozzle is too small, it's not going to have enough force to overcome the static friction, therefore it doesn't move. If the nozzle is too big, it's going to have too much force and it can cause the car to tip over. Here we have a video of this. You can see the back wheel slightly lifting off. So within our range, we found that the larger nozzle diameter is better. Here we can see that the energy input equals work to inflate, and in the next page we're going to see how we used this formula. So this graph is demonstrating how a balloon is inflated. Now we're making some pretty big assumptions here that everything is linear, because it would be almost impossible to calculate if it isn't. So from this we're only really going to be able to see trends. So as you can see, rubber doesn't inflate like this because the balloon's going to deflate differently than it inflates. This is hysteresis, and it's also going to be time dependent. So we have energy input equals 1/2 of pressure times volume. That's what we used. So it's important to note that we only used every balloon once, just to reduce the effects of hysteresis. And next to this we can see a graph of what hysteresis may look like. We were able to keep our balloon circumference consistent by using a piece of string that was 60 centimeters in length. We were able to measure the pressure of the balloon by using a pressure sensor, and we use this in our next graphs to calculate the efficiency. Here we have the efficiency of the car, which is the energy output equals maximum kinetic energy of car, and then we have our maximum kinetic energy equals 1/2 of mass times maximum velocity squared. Here we're able to calculate the efficiency of how far the balloon went and the maximum kinetic energy or velocity. So by using these formulas, efficiency percentage equals energy output over energy input times 100, we're able to find a percentage of the efficiency, so how much energy was wasted, which we'll be able to see in the following graphs. And then we have our efficiency equals mass times velocity squared, maximum velocity, over pressure times volume times 100, and that also gives us a percentage. So we have some keys down here of the units. Mass of car was measured in kilos, maximum speed was measured in meters per second -1, pressure was measured in pascals, and balloon volume in meters cubed. Another important thing to note is that the pressure we used, atmospheric, is pressure above atmospheric. So here's our graph of our maximum speed. We can see that our 6.5 millimeter nozzle reached a maximum speed of around 0.6 meters per second. Now there is quite a big jump to the next nozzle size, and comparing the 19 millimeter and 21 millimeter, considering the error bars, it's slightly hard to tell, but the 21 millimeter still does reach a higher maximum speed. Here's our maximum kinetic energy graph. Here we see our small nozzle diameter it's not efficient. It wastes quite a lot of energy, whether that be through friction. So small nozzle diameter is out of the question. We don't want to use that if we want an efficient balloon car. But as you can see from our higher nozzle diameters, they're a lot more efficient as they reach high kinetic energy. And the nozzle diameter efficiency, you can see our small one really isn't efficient at all. However, our higher ones, they appear to be a lot more efficient based on the data that we took. So here's our distance travelled graph. You can see that our 6.5 millimeter hasn't travelled super far, but as you can see in our 19 millimeter and 21, they've done a lot better in terms of distance, making them more efficient. So our conclusion of our parameters: within our range tested, increasing the nozzle diameter increases both efficiency and distance travelled. Now it's important to keep in mind that this is only in the range we tested. If we had gone up further in nozzle diameter, we predict that there may be more lifting of the back wheel, which is not going to increase the efficiency. So that's important to keep in mind. Acknowledgements, references. Thank you.